So in this video, we're going to look at an example of actually determining the shear and bending moment diagrams for a beam. So here we have a beam, which is simply supported with a pin on the left and a roller on the right, and we have a distributed linear load tapering up to a maximum value of 6 kilonewtons per meter, and we want to draw all the shear and bending moment diagrams. And remember, those are nothing more than how the internal forces V and M vary as we move along the beam. So the first step in all of these problems is actually to determine the external reactions on the beam. And since beams are always loaded with perpendicular loads, it's not surprising that even though that pin could have a horizontal external reaction, we actually don't need to solve for it. Sorry, I'm just making sure that we're actually recording. Good, we are. If you wonder why I'm doing that, I actually went through the whole video previously and had to start from scratch. So I'm going to draw in vertical reactions on both ends of the beam, and I just call them A and B. I'll take off the Y because, again, as we mentioned, this could have an X component, but it doesn't need it. In addition, I need to, from the perspective of solving for my external reactions, replace that entire distributed load by a single concentrated force. And the triangular distribution, or that linear taper, is something that we've dealt with quite a bit until now. So if it has a density function who has kind of a base, you can say, of 9 meters and has a height or a peak value of 6 kilonewtons per meter, remember that the only thing we really need from this is the area under that curve, or the area of this triangle, because that gives us the magnitude of our distributed force. For a triangle, or I should say our concentrated force, for a triangular load, that will just be 1/2 the base times the height, which is just going to be, if we cancel a 1 and a 3 there, 27 kilonewtons. And remember, we're going to apply that at the centroid of the shape, which is just going to be 1/3 of the way from the side with the peak value. So if this is 9 meters long, we'll put a 3 meter force of 27 kilonewtons at that point. And what that's going to allow us to do is to solve for these two reactions. I can solve or isolate the reaction at A, or I should say the reaction at B, by summing all moments about point A. You could do it the other way as well, if you'd like. And if you sum all moments about point A, what you find is that the reaction at B actually induces a counterclockwise rotation, which is positive according to our convention. Remember that the beam is 9 meters long, so that perpendicular distance for the reaction at B is 9 meters, so it's just going to be plus 9 times B. In contrast, if we look at the rotation associated with this 27 kilonewton force, that's going to be clockwise, so that's negative according to our sign convention. Its perpendicular distance from A is only 6 meters, so it's going to be minus 6, and then we know the magnitude of that force is 27. So that must all equal to 0. So what that tells us is that B is just going to be 6 times 27 divided by 9. If you do 2, and you do 3, and you do 1, and you do 9, I think that comes out to be 18 kilonewtons. And then we can solve for the reaction at A then by simply summing all forces in the Y direction and setting that equal to 0. And that shows us that A and B going up have to equal the 27 kilonewton force going down. So we already know that B is 18 kilonewtons. So A is just going to have to take whatever is left over of that, which is going to be 9 kilonewtons. So that's actually going to allow us to solve for the reactions of each of these supports. And that's going to be the first step in order for drawing the shear and bending moment diagrams. So as I mentioned in the last video, what we need to do now, since this distributed load is continuous throughout the entire span, is just segment or pass a section through the beam in some arbitrary section of length x. Now notice if we're moving from the left, that section will be subjected to the reaction at A, which we've already solved to be 9 kilonewtons. And then all that I need to do is just draw in my internal force system. And remember, again, not to beat a point repetitively, but since beams are always loaded in the perpendicular direction, this internal force system in this case is only going to have a shear force and a bending moment. So basically all that I need to do is to solve for these two quantities given the reaction that this portion of the beam is subjected to, but also the portion of the distributed force. And that's one of the challenging things that people struggle with sometimes, because they look back at the original free body diagram that we used to solve for the reactions, and they say, hey, there's no at some arbitrary x before I get to 6 meters, there's no force applied. But remember that distributed load is actually subjected across the entire beam. And when we originally talked about kind of the idea of replacing a distributed load by a single concentrated force, we said that that was only valid for actually determining external forces like reactions. So when we want to determine these internal forces, we have to again consider it as distributed. But one of the other tricky things is, if we want to actually solve for V and M, we don't know how to do that for a distributed force. So even though we have to reconsider the distributed force again, the next thing we have to do is actually replace it by a single equivalent force. And this is where it gets tricky. Because if you think about it, if you're trying to calculate the area under this curve, what is the area under the curve? Well, it always helps to just start drawing and say, hey, do I have the information that I need? Well, you know that this base is going to be x units long. But the question is, what is the height going to be? Well, remember, if this entire distributed load over a 9-meter span, so this is 9 meters, has a peak value of 6 kilonewtons per meter, then I can say that the slope of the distributed load curve is going to be nothing more than the rise over run, which will be 6 divided by 9, or 2/3. And what that means is I can find the height of the distributed load curve at any point by just saying 2/3 x. So if I know the height of this triangle and I know the base, remember that the area is always 1/2 the base times the height. So what that means is I'm going to get 1/3 x squared as an expression for the single concentrated load that needs to be applied to this beam at a particular point. Now the question is, where should the point be? So let me actually start to draw this in a little bit. We have 9 kilonewtons, the reaction at A. We have our unknown shear force. We have our unknown bending moment. We know that we need to replace this by a single concentrated force with magnitude 1/3 x squared. But the question is, where should it actually be located? Well, if this distance is x, right, this entire distance, I've chosen to cut it at an arbitrary x, then I'm going to simply apply it at 1/3 x. So I'm going to have that single force, which is going to have a magnitude of 1/3 x squared. Now this looks a little bit funny as a free body diagram because it has forces and parameters that vary as a function of x. But I know, based upon the kind of discussion that I did in the prior video, that this is the way I need to approach it in order to get expressions for V and M that vary as a function of x. And these are going to be valid for any x. Let me write that in. From 0 to 9, why? Because there's no discontinuities in the actual distributed load, and there's no concentrated forces that just appear out of nowhere, as will be the case in one of your actual homework problems. So I'm going to go back to the PowerPoint now just to keep this video a little bit short. It's already at 7 minutes, and I have the solutions from the text slide actually typed in here. But the one thing I wanted to show you is note that they've replaced the magnitude of that concentrated force by 1/3 x squared. The same thing we got. They're applying it at x divided by 3, or 1/3 x from the right side of the beam. We have our shearing force and we have our bending moment that we're trying to solve for. And there's our reaction. We're going to do it the same way I always do it. We're going to sum all forces in the y direction. That's going to allow us to solve for V. Notice it up, we have 9 kilonewtons. Down, we have the V we're trying to solve for, along with the 1/3 x squared. So when you actually make that summation, what you see is that the shearing force is going to vary quadratically, right? That's what x squared function looks like as a function of x according to this expression. Now, when you actually go to solve for what this internal bending moment is, if you sum all moments about that point, note that that 9 kilonewton force is going to induce a clockwise rotation at some distance x. So we should have a term that looks like minus 9x, and we do. It's right here. We have the unknown m that we're trying to solve for, which by our positive sign convention is in the counterclockwise direction or positive. The only thing that we need left to do is to determine the rotation about that cut point of the concentrated load corresponding to the distributed load. It's a mouthful, but if you note, it's going to rotate it in the counterclockwise direction, so it will be positive. Its magnitude is 1/3 x squared, and its perpendicular distance is x over 3. So that's actually going to leave in the moment term to a term that actually involves a cubic, or x cubed. So if you do all that correctly, what you will find is that the expression for the bending moment as a function of the distance across the beam is actually cubic, but it also has a linear term as well. So that's how these individual expressions were come up with, and you can see some plots of them over to the actual right here. So one of the things that is usually interesting from kind of a point of view once you have these functions is oftentimes to find their zero values or to find their maximum values. And that's just a matter of applying some basic mathematical concept. So we will talk about these a little bit more, maybe if we have enough time to do another example or lecture video in this section. My preference is that way we can move on with the course to kind of just leave this here, but it is a concept that you will see again. So just note the general procedure for doing it. When someone says shear or bending moment diagram, what they're talking about is finding an expression for how those two internal forces vary across a beam. Remember the idea of what beams are, and remember that these diagrams are useful, particularly for designing the cross sections of beams.